Hello there. Um, I apologize if I sound like I have something plugging my nose, but I do. I'm very stuffy today, so I'm going to do the best to try to speak clearly. And we're going to work through this last section of Chapter 9. This whole chapter has been about quadratic functions, and been doing a great job of solving quadratic functions different ways, like by graphing, um, by factoring, by the quadratic equation, lots of different ways. And specifically in this section, um, we're going to talk about systems of a linear and quadratic equation. We've done systems of linear equations before. That was a whole chapter in and of itself, and we had three different methods. Today we're going to use those same three methods, but one of the equations is going to be a quadratic equation. All right, so our objective is to solve systems of linear equations, at linear and quadratic equations. All right, first of all, um, looking at these graphs. When you look at graphs of equations, we have one linear and one quadratic. A lot of times we're going to have situations where we have two solutions. Okay, that's where the quadratic equation and the linear equation cross at two places. You can see here, it's wherever they would cross out. Those would be the solutions. We could have one where it's just one solution, where they cross at one point on the graph. And then also there are times when we could have no solutions, where they never cross. So we'll have different situations where those will take place. So keep that in mind. That's how we look on the graphs. And in general, when we're solving by graphing, what we're doing is we're trying to graph both equations and see the points they cross. And sometimes it'll be very clear. And here is a procedure for it. The big thing is just remembering how to graph both quadratic and linear equations. So first, graph the quadratic function. So find the axis of symmetry. Um, So to find the axis of symmetry and also the vertex, we do that, I don't know if I have it on here, but we do minus b over 2a. So we call minus b, the b value, the negative of b value, divided by 2 times the a value, to find the x. And then we can plug that in to find the y. Okay? That would be finding the vertex and the axis of symmetry. Then we want to select two values on one side of the equation and plot those. So we're going to have to plug in two x values on one side and then reflect them across the other side of the axis. That's how you graph the quadratic. Graphing linear equations is hopefully a little bit easier to remember. We want to graph it using the y-intercept and the slope. All right, determine whether there's where they intersect, and that would be your solution or solutions. So I'm going to try one of these together and maybe have you do the other one on your own. All right. So to graph the quadratic, we don't actually have a b value if you see here. So I'm going to rewrite this as y equals 2x squared plus 0x plus 1. So in descending order there. And we have that gone now. So to find the vertex and the axis of symmetry, we're going to do minus b, so negative 0 over 2 times 2, which is going to be 0. So our vertex is going to be 0, and if we plug that in for each of these parts, that first part's going to be 0, the second part's going to be 0, and we just have 1. So 0, 1 is where it's going to start, and it's going to go up and down through there. So I'm going to pick two values now, remember, on one side of that so that we can graph a couple of values and then reflect them. So let's do this. Chart x, y. So 0, 1, let's do 2 and, 1 and 2 for our x values. So plugging in 1, we've got 2 times 1 squared. Sorry about that. Plus 0 plus 1. So that's going to be 2 times 1, so that's going to be 3. So we have the point 1, 3. 1, 3. Plugging in 2, we'd have 2 times 2 squared. 2 squared is 4, times 2 is 8. Plus 1, we'd have 9. So 2 and 6, 7, 8. So it's going to be up here-ish. And we just want to reflect those over so we have the points on the other side. So this is going to be right here. This one's going to be approximately right here. And we have our graph that looks like this. Not perfect. It's hard to get it perfect if you're not using a graphing calculator. But now we can graph our other line. And hopefully we can find points of intersection. Negative 2x plus 5. So we're going to start at 5. 1, 2, 3, 4, 5. Go down 2 over 1. And down 2 over 1. We want to go backwards to see where it intersects over here, too. Up 2 and over left 1. Up 2 and back left 1. So it looks like we actually intersect at 1, 3. And negative 2 and 9. So those would be our two intersecting points, our two solutions. And let's see if we were right. Negative 2, 9, and 1, 3. Nice. All right, we got it. So what I'd like you to do is to pause it and try. So if you want to pause this and make sure you have all this work written down, but I'd like you to try doing the second one on your own, and I will reveal the results in just a second. So pause it here. All right, so looking at this one, when I graphed the quadratic, I found the vertex to be negative 1/2 and 2 3/4, and then I used 1 or 0, 3, and 1, 5 on the one side and reflected them across. That's in the green. And then the linear equation y equals negative x just goes through the origin and has a slope of negative 1. So if you look at the graph, they'll never cross, and that means there is no solution for this one. So that's the graphing method for solving systems of equations. Second method is the elimination method, which is very similar to the elimination method that we have done for um, systems of linear equations. So here's an example. It says, since opening day, attendance at pool A has increased steadily, while attendance at pool B first rose and then fell. Equations modeling the daily attendance at Y at each pool are shown below, where X is the number of days since opening day. On what day or days was the attendance the same at both pools? So if we were to graph them, we'd see exactly where they would cross, where they'd be the same. But here's the two equations. Y equals 28x plus 4, and y equals negative x squared plus 39x plus 64. All right? Using the elimination method, we want to set them up so that we can eliminate one variable, and then have the other variable, and then we can plug that in and solve for it. So if we have our quadratic equation, y equals negative x squared plus 39x plus 64, we want to do that first. And then we have our linear equation. Remember, they have to all match up, like the parts do. So in a linear equation, there is no x squared term, so we just leave that blank here. Okay? Make sure all the other ones line up, though. And since we want to cancel out the y, let's always cancel out the y in this case, we subtract. Because you don't have to do much any more work if you're doing that. So subtract everything, cancel out the y. We'd have negative x squared because nothing happens to that. Subtract the 28x from the 39x, so you get 11x. Subtract the 4 from the 64 and get 60. So we have 0 equals negative x squared plus 11x plus 60. Now there's no y's, so we can solve our quadratic function to get our zeros, to get our x's. So we're going to factor and solve. This one we can factor out a negative. And then what's left would be x squared minus 11x minus 60, and that factors to x minus 4, x minus 15, or our zeros that if we solved it, sorry, x plus 4 and x minus 15, are going to be negative 4, we set them both equal to 0, and 15, okay? And for this specific problem, you can't have a negative because pools cannot open a negative number of days. So the solution for this one would have to be 15. So after 15 days, they had the same attendance. And you can plug back in the 15 for the x to get y, which would be attendance of 424 people. Okay? So here's the procedure written out for you for using the method of elimination. Write both equations in descending order and line up the like terms. Like we said there, the linear one is not going to have an x squared. Subtract the equations to eliminate the y value. Factor the remaining equation and set both parts equal to 0 to solve for x. So we gotta factor it. If you really can't factor it, there's other methods to solving, but it should always work to factor in the problems that you'll be given. Eliminate the possible solutions if there's a negative. If it's a word problem, you typically can't have a negative. Um, and substitute the x or the x values back into the linear equation and find the y value that goes with them. So let's try it. I would like you to try this one on your own. I'm going to do it as well. And um, if you get stuck, you can certainly unpause it and check. But why don't you pause it, and I'm going to work through it as well. So it says, suppose the daily attendance y at pool A can be modeled by the equation y equals 36x plus 54. So we're just going to use the same one as before for the pool B. So we have pool A is y equals 36x plus 54. Pool B was negative, let's just go up and check, negative x squared plus 39x plus 64. That is a 39x. Let's just double check that I did that right. Yes, I did. All right, so we got to line it up. So I'm going to take the second one, move it on down here, but I'm going to line them up. Y equals nothing plus 36x plus 54. Okay, so now I want to subtract this whole thing. And when I do that, I get 0 equals negative x squared, subtract there would be plus 3x, subtract there would be plus 10. Alright, let's pull out that negative so we can factor this. So we have 0 equals negative 1, and we just have x squared minus 3x minus 10. Alright, so let's factor that part. Numbers that multiply to equal negative 10 and add to equal negative 3. I think it is negative 5 and 2. Well, there we go. So, we have x minus 5 and x plus 3. Sorry, 2, not 3. 2. And when we set them all equal to 0, the negative 1 kind of just goes away. And we have x minus 5 equals 0. This is the 0 products property. X plus 2 equals 0. And you subtract 2 from the right one, add 5 for this one. And you end up getting x is equal to 5, or x is equal to negative 2. So now realizing that this is a pool, and you can't have negative days, this one is out. So we know it's 5 days, and we can plug back in for here, and here, or you can plug it into either equation. Yeah, or you can plug it into here, and I'm going to do it in the top one. I think that'll be easier. I'm going to say y equals 36 times 5 plus 54. Take out your handy-dandy calculator and find out that 36 times 5, and you add 54, you get a total of 234 people in attendance. Did not take long for them to have the same amount of attendance there. Alright, so that's the the elimination method. Substitution method is, again, very similar to the substitution method that we've done before. So we'll go through an example. I'll give you the procedure and have you try it. Let's take a look here. Remember, for substitution method, we want one of them equal to either x or y. And in this case, they both are. So what we're going to do is we're going to plug in this, since this is equal to y, in for y over there. Okay, so we really have 4 minus x is equal to x squared minus 6x plus 10. So we can set the two equal to each other. And we want 0 on the one side, so let's subtract 4 from both sides. And add x to both sides. You end up getting x is equal to x, or 0 is equal to x squared minus 5x plus 4. So now here, this is a good place to be, because this is a quadratic that's set equal to 0. So that we can find the zeros of it by factoring. All right, factoring it, you get x minus 2 times x minus 3. Set them both equal to 0, and you'll get, oopsie doodles, you end up getting 2 and 3 as your results. So we got two x values, so we'll have two solutions. But what we have to do is plug each of them back in for the one of the originals to find the y values. So it doesn't matter which one you plug them in for, but you get the y values of 2 and 1, so we get 2, 2, and 3, 1 are our results. So what we did there in words is we wrote one equation combining, or one equation combining both functions by setting them equal to each other. So we have that takes away the y value because we set them equal to each other. Move all terms to one side, getting only 0 on the other side, and then factor. And when you set all terms or set them equal to 0, we find our x values, and we can substitute them back in to find the y values. So here's the last example we're going to do, and then I'm going to leave you to yourself for this section. This is the last section again. So what we're going to do, it says, what are the solutions of the system? So if you notice in this one, it's kind of tricky because this one's not even solved for y. So let's add 30 right away. So we get y equals 12x plus 30. And now we can set them equal to each other. So we have 12x minus, or plus 30 equals x squared plus 11x minus 12. Okay? We want to get rid of both these things from both sides. So minus 12x. And we also want a minus 30. So we have 0 is equal to x squared minus 1x minus 42. And we need to find 2. Now we need to factor it. So what can we factor this so that we have it equal to, let's see, multiply to equal to negative 42. Add to equal to negative 1. I think it's going to be 6 and 7 or negative 7. So we'd have x plus 6 and x minus 7. And then when we solve each of them by using the zero products property, 0x equals x plus 6, 0 equals x minus 7, we get x is equal to negative 6, and x is equal to positive 7. Okay, we're not quite done because we need to solve them yet, but we have our x values. So negative 6, we got to find the y value. So we have two solutions again. And 7, we just got to find the y value. So why don't we plug it into this one. So y equals 12 times negative 6 plus 30. And then y equals 12 times 7 plus 30. Calculator, 12 times negative 6. 12 times 6. 12 times negative 1. Whoops, I did something wrong there. Plus 1. Making that a negative. And then we want to add 30 to it. You get negative 42. So there's our first ordered pair. And then our second ordered pair is 12 times 7 plus 30. Is 114. So we have 7 and 114. Some very large numbers here. I'm glad we didn't graph this one. And we did get the same results there. So depending on the situation, depending on which one is your favorite, there's 3 different methods for solving. And you should know each one of these 3 methods. Okay? You may end up liking one more than the others, but it's good to know all 3 of them. Graphing, eliminating, and substituting. All right. Um, there is a way to do it on a graphing calculator. We're not going to necessarily go through this because my guess is you do not have a graphing calculator. Um, but I would like you to know that if you ever have one, there's ways to play around with it and do this on a graphing calculator. It's pretty fun. But that brings me back to our goal, which is to solve systems of linear equations, systems of linear and quadratic equations. And we had 3 different methods to do that. So we'll see you next time.